Hi, welcome to this video series on cryptography. Today I'm going to talk about the Chinese remainder theorem, which has many interesting applications in cryptography. I will briefly introduce the theorem and then I'll talk about the applications of the theorem, for example, doing basic arithmetic. Okay, let's get straight into the theorem. Okay, suppose you have two prime numbers p and q. We can do some simple computations easily, right? N equal to p times q. If n is a composite number, p and q are primes. What we can do with this Chinese remainder theorem is quite fascinating. Suppose you would like to do computations in, say, Zn, which is made of numbers from, what are the numbers in Zn? Zn is made of numbers from 0 all the way to 1, 2, n minus 1, right? All the integers, no fractions and decimals, whatnot. Okay, so these are the numbers of Zn, right? And what is the benefit of Chinese remainder theorem? The Chinese remainder theorem helps us to map the elements of Zn to another interesting group. Okay, so what I mean by interesting group is this: you can map the elements of Zn into this particular group. I'm just getting used to the automatic pen writing using this technology, but anyway, so we are mapping our elements from one group to another group. Okay, what it means is that if you have an element x in Zn, we can do a simple computation like this. We can compute x mod p, right, and x mod q. Okay, that basically is the mapping. So every element gets mapped to the remainder when you do mod using the p and q respectively. Okay, so you have basically a pair of elements for every element x in Zn. So what is the big deal about this? The benefit is this: the p and q are much smaller than n usually. Well, because p and q are product of p and q itself are multiplied to form n. Therefore, p and q must be usually half the size of n. So we can do computations much easier in smaller groups and then transform it to the original group. So what it means is that suppose you would like to add two numbers x and y in Zn. What you will usually do is you will do x plus y mod n, right? That's how you do it. But in this case, you transform your x to x mod p, y to similarly y is also going to be transformed like this, right? Y will also be transformed into an element in y mod p and y mod q. Okay, so what can we do now next? Once you have these pairs, well, we can add the corresponding components to form x plus y. But again, x plus y is not in Zn yet. Okay, so if we add these two things, let's do a plus, right? The regular plus. So what will happen now? You have your components added. You add your components x plus y, and you have to do mod p because the answer may exceed p. And then the same thing for the second component. Okay, what is the second component? The second component is this x plus y mod q. Okay, so how do we now get back from here to a point on Zn? How do we do that? So here comes some neat tricks that we can leverage. So the idea is that we can transform elements from Zp, Zq to Zn by doing a simple transformation like this. Okay, let me create another drawing, and we can transform x plus y mod p, x plus y mod q back to an element in Zn. So how do I do that? I will select my point like this. The point is going to be, suppose I have a point a comma b. How am I going to get back to the original elements in Zn? So I can rewrite my x a comma b as a times 1 comma 0, right, plus b times 0 comma 1. Okay, so the question now is, how do I get the 1 comma 0, 0 comma 1 mapped back to the Zn? I can take 1 comma 0 and get back an element easily in Zn as follows. Now comes this p and q being primes, helping us to find two other numbers. We can find easily So suppose you have P and Q being prime, we can use extended Euclidean algorithm to find other two numbers X and Y such that this is equal to GCD of P comma Q, which is 1 because P and Q are relatively prime. Okay, so what does this help us? Okay, how does this help us? This is going to help us by helping us to map 1 comma 0 as follows. So we can take XP, right? XP is what? XP is same as 1 minus YQ. Okay, 1 minus YQ. So which means that what is our XP mod Q? Well, XP minus mod Q must be 1 because YQ will get cancelled out when you do mod Q, right? Because YQ is multiple of Q. So this is going to be simply 1. Okay. What about YQ? YQ is same as, similarly we can write like this: YQ is equal to 1 minus XP. Therefore, YQ minus mod P will be 1. Okay. So this is the foundation that we need for our problem to map 1 comma 0 back to an element in Zn. So once you have this, we can do now very simple calculation. So what is the value of XP in mod n? Well, we can map this to Z. Okay, let's look at this. How do we map this now back to an element in P comma Q pair? So this is nothing but XP mod Q. XP mod Q is just 1. I have just shown you on the right hand side, 1 comma 0, right? Because XP mod Q is 1. XP mod P is 0. So I made a small mistake. So this is 0 and this is 1, right? Sorry for that. So XP mod n is nothing but XP mod P, which is 0, and XP mod Q, which is 1. This is because of this. Okay, so it's to be more clear, it's 0 comma 1 pair. Okay, so this is 0 comma 1 pair. Okay, so this, let's call it as XP mod n mapping to 0 comma 1. So if you do the same for your YQ, right? What will happen now to YQ mod n? YQ mod n, we get transformed into, first we do YQ mod P. What is YQ mod P? YQ mod P is 1, right? This is YQ mod P, which is 1. So we get 1. And what is YQ mod Q? Because YQ has obviously Q inside, so it will get transformed into 1 comma 0. Okay, so we found out how to go, transform 0 comma 1 from this group, right, into Zn. So we know how to go from 0 comma 1 and similarly from 1 comma 0 to the original group. So we can now go back to this equation, right, and we just plug in this number. We know 0 comma 1 is same as XP mod n, and 1 comma 0 is Y times Q mod n. Okay, through extended Euclidean algorithm we can find this X. Well, this is the extended Euclidean algorithm that will help us to find capital X and capital Y. So we know everything now. We have capital X, capital P, capital Y, capital Q. So we found out the values of 0 comma 1, 1 comma 0, okay, in the corresponding group. So once we have this, this has to be, of course, computed back into mod n. Okay, otherwise you will not be able to get back to an element in Zn, right? Remember, 1 comma 0 is already mapped to an element in mod n. This is YQ, and 0 comma 1 is XP. Okay, so all you have to do is A times 1 0, B times 0 1. You're done. Okay, so far I explained the mapping from Zn to ZP, ZQ, and vice versa. How is this going to help us in doing computations faster? First of all, you need to convince yourself this is one-to-one mapping. So that comes from basic rules of modular arithmetic, and primes being P and Q will help you to establish the fact that this particular transformation from Zn to ZP, ZQ pair is actually a one-to-one function. So I'm not going to give a proof for that, but you can take it for granted that this is a one-to-one function. Okay, so with that background, now let's do some simple computations and convince ourselves that we can do addition in ZP, ZQ pair and get back to original answer. Okay, this is kind of a homomorphism. This is actually homomorphism. Okay, so I'm going to share my Python implementation with you and show you this implementation details. So I wrote a Python implementation myself, Chinese reminder theorem. Extended GCD algorithm, as I said, is needed to find the capital X and capital Y. By the way, the variable names are slightly off, but should not confuse you anywhere. So all I'm going to do now is directly show you an execution and then we run it. Okay. So I will start my Python interpreter, right, from CRT, Chinese reminder theorem. I'm importing all of this. Okay. Chinese reminder theorem. What is this? It says no module found. Okay. Sorry, one moment. I need to change to my folder and now it should be there. So import from CRT. I'm importing all my modules, right? And I'm going to create some simple groups to play with. Let's say P being 5, Q being 7. So what is N now? N is P times Q, 35, right? So let's do some simple addition. Let's say my X is 8 and Y is 12. So what is X plus Y? X plus Y is 20, right? Obviously, answer is simple. 20 in mod 35. Okay, so we can print X plus Y mod N. Okay, now let's do the same by transforming the X into an element in ZP and ZQ pair, and the same for Y. Okay, so how do we do that? So all we are going to do is we are going to create a new pair, right? What is my XP? XP is nothing but X mod P, right? And which you can check for yourself. 8 mod 5 is 3. And what about XQ? Transform the point X into Q. Okay, 8 mod 7 is 1. So we can print and see for ourselves this is the case. Okay, XP and XQ, right? So 3, 1, as I explained. So let's do the same for Y also, right? YP is equal to Y mod P and Y mod Q. Okay, so we are now going to add the corresponding components. Okay, so XP plus YP, I call it ZP. Okay, to avoid any confusion, I call it sum P because we are also using XY for some other purpose. XYZ will confuse. Okay, so XP and YP, right? But we have to do mod P because we're still adding the corresponding components, and sum Q is XQ plus YQ in mod Q. Okay, so far we added the components. We have now one pair in ZP ZQ. Now we need to get back. We need to transform our sum P sum Q pair into a unique number in Zn. That's what we need to do. So how do we do that? Here comes the Chinese reminder theorem trick. So I will call the Chinese reminder function CRT, and I will pass the X component and the Y component, and then I will pass my P and Q. Hopefully it will show the answer to be 20. Yep, here you go. So it's a 20. This is 20. This is the original number if you add it in the original group, and here's the transformed group, and then we get back to the original group. So how is this happening? This is exactly based on the idea I explained to you on the drawing board. Essentially, here is the logic, right? It takes our P and Q. We can now go through this, right? It takes our P and Q. Of course, it takes our XP and XQ components as well. It computes the product of the prime numbers, and then it computes the 1P and the 1Q. So what is this 1P and 1Q? Remember how to compute 1P and 1Q? Essentially, using the extended Euclidean algorithm, we find what elements can be mapped to 1, 0 and 0, 1. That's basically it. The inverse of 0, 1 and 1, 0 are computed. And then we apply the Chinese reminder theorem to combine those 1P and 1Q and take mod N, as I explained on my drawing board. Okay, so this is basically it. This is Chinese reminder theorem essentially. So in practice, oftentimes we need to call Chinese reminder theorem many times in cryptography. So usually what happens is people compute 1P and 1Q only once because they don't change P and the Q are fixed. One P and one Q will not change. So that's why I have another wrapper. So you can also compute this once and keep calling the Chinese reminder 2 once you know these two numbers. Okay. So anyway, this is for plus, right? We can also do the same for multiplication. It doesn't change the setup. So let's try. Now let me remember what is P and the Q for you. P and the Q. So we have P being 5, Q being 7. So PQ is 35. Let's take some X, okay? Let's take X to be 4 and Y to be 7. So what do we expect the answer to be? Well, let's take Y to be 9. Okay, now in mod 11, let me do this, X times Y, mod 35 rather, right? Because P comma Q, okay, is 35. So answer is 1. So shall we see whether we can get 1 when we transform our points P and Q, our points X and Y rather, to ZP and ZQ. So what is the first thing we do? We take X and compute mod P, right? And we do the same for mod Q, okay? And we do the same for YP. So essentially we are transforming our points from one group to another group, and YQ, okay? So now we have to do multiplication across the individual components, right? Let me call it product product XP, yeah, product X is equal to XP times corresponding component, right? YP. Let's call it product. It's not. So we do product in mod P, and the same with product in mod Q. I should be able to get the 1. Yeah. So I made a small mistake here, and that confused. Okay. Anyway, so we now figured out how to compute in subgroup and get back to the original group's answer. It's the same answer, right? Instead of doing multiplication in the original group, I'm doing it in a small group. The actual benefit of Chinese remainder theorem actually is in exponents. Okay, when you do multiplication in exponents, for example, in RSA or in Diffie-Hellman, in particular RSA, we do a lot of multiplications in exponents when you do decryption. And instead of doing a decryption in Z and star, we do transform the points into ZP and the ZQ star respectively. And then we do the transformation back using this Chinese remainder theorem trick. I will explain how that is used in RSA later, but this is basically the purpose of this demo, to show you Chinese remainder theorem is a pretty cool idea to map points from one group to another group and transform the results to the original group. Okay, that's basically it. Thank you very much.